Hello. Today I'm going to describe Prophecy, which is a new approach for optimizing mobile page loads. So I did this work with my co-author Ravi. I should note that he is on the job market. You should hire him. I should also note that I'm going up for tenure next year. I hopefully won't be on the job market. But just in case, let me give you some quick facts about James Mickens. I have $3.2 trillion of NSF grants. I love to teach huge introductory courses like data structures for non-STEM majors who can't math good. And for all you professors out there, I will gladly park my car farther away from the parking lot so that you can be closer to the department. So I'm James Mickens. Get to know me. This advertisement has been sponsored by Late Stage Academic Capitalism. So anyways, we got about 19 minutes left, so let's talk about mobile browsing. So mobile browsing is obviously very important. Recent empirical studies have shown that smartphone usage consumes about 63% of user focus time with respect to browsing. And browsing also consumes about 54% of overall CPU time. So in fact, mobile browsing actually generates more HTTP traffic now than desktop browsing. But alas, mobile browsing is actually a challenging technical space. And the reason is that a successful mobile browsing experience requires you to optimize for a bunch of different metrics. So one important metric is actually page load time. So we all know that slow pages make users angry, and search engines actually assign lower ranks to pages that load more slowly. So slow pages generate less revenue for page owners. So reducing page load time is an important metric. Furthermore, we want to reduce the bandwidth consumption of mobile web pages. The reason is that many users have data plans which actually charge users according to the amount of network bandwidth that's consumed. So even so-called unlimited plans oftentimes impose rate limits once the user has hit a certain traffic cap. So reducing bandwidth consumption is also important. But there's yet another important optimization metric that is important as well. So who hasn't experienced the joy of your phone buzzing and you think, how exciting, I've just received a new email or Snapchat or Pokemon, and then you check your phone and you discover that you are merely low on battery life, right? This, of course, is the saddest Pokemon of all. So how does this relate to web page loading? Well, a browser actually requires energy to fetch data over the network or to parse HTML or to execute JavaScript. So in this talk, we're going to look at a single high-level question. Can a single optimization technique reduce page load time and decrease bandwidth usage and minimize energy consumption? Now, fortunately, the answer is yes. And the insight that we're going to leverage is that web browsers can elide intermediate computations during the page load process. So in a traditional page load, the browser is going to download a bunch of content, and as that content arrives, the browser is going to parse and evaluate it, generating a bunch of intermediate results. So in our new system called Prophecy, a client's going to download a write log that contains the final value for each piece of state in the page. The client can then parse and evaluate that log, skipping over the intermediate results and directly building the final version of the page. So Prophecy optimizes all three metrics that I mentioned. It's going to reduce median page load time by 53%. It's going to decrease bandwidth usage by 21%. And it's also going to cut energy usage by 36%. So basically, everyone's a winner except for the anime boy who's trapped inside the triangle, but not everyone can literally be a winner. So let's not try to focus on that. So here's an outline for the rest of the talk. So first I'm going to give you some technical details about how page loads have traditionally worked. Then I'll describe the architecture of Prophecy and evaluate its benefits. And finally, I'll briefly discuss some related work before concluding. Okay, so let's start off by looking at the kinds of state that's inside of a frame. Note that a single web page consists of one or more frames. So for the purposes of this talk, we can assume that the browser assigns a JavaScript engine and a renderer to each frame. Now off to the right, we're going to have some web servers. So when the user decides to load a particular frame, the browser sends a request to the web server and then receives some HTML in response. So the renderer is going to start parsing that HTML. Now, as the parser executes, the renderer is going to incrementally build something called the DOM tree. The DOM tree is a C++ data structure that mirrors the HTML structure of a frame. So there's a single DOM node for every HTML tag that the renderer has discovered. So the HTML parser is going to continue, find the CSS tag and the script tag. The browser is going to issue two HTTP requests for those two external objects and then receive those two files. So when the browser gets the CSS file, then the browser is going to change the style of those flashing DOM nodes up there. And when the browser gets the JavaScript file, the browser is going to pass that file to the JavaScript engine at the top of the slide. The JavaScript engine is going to evaluate that source code and then build the initial set of heap nodes shown at the top of the screen. The HTML parse continues. We find the image tag. We're going to build the new DOM node for the image tag and then go out and fetch that. The HTML parse continues, and at some point, the browser asynchronously is going to receive the response and then update the display as appropriate. So meanwhile, the parse continues. The browser discovers the final script tag, issues a fetch for that, hands it off to the JavaScript engine at the top. And what the JavaScript file will do is perhaps it will create a few new JavaScript heap nodes, and it may also modify some of the pre-existing heap nodes or actually get rid of some of them. So at this point, the frame is now completely loaded. So what do we just learn? Well, what we saw is that the process of loading a frame is actually this process of incrementally building these two data structures, the JavaScript heap and the DOM tree. So a natural question is, why can't we just skip to the final step? Why can't we just have the server send the final version of the frame to the client? Well, I'm here to tell you that you can skip to the final step. However, and this is very important, the solution is not the blockchain. Anybody who mentions the blockchain gets dragged out of the session, no questions asked, you'll thank me when you're older, okay? So here is what the solution is. Okay, the solution is going to be prophecy. So first we're going to look at how a prophecy server determines a frame's final state, and then we're going to see how a client recreates that final state. So here we're going to look at the server side of prophecy first. So on the left we see the prophecy server, and on the right side there's a web server which generates the content in a frame. Now in practice we can run the prophecy server on the same machine as the content server, but I've separated them here to make it clear what prophecy does. So the prophecy server is going to run a headless browser like Phantom.js. A headless browser is just a browser that doesn't have a visual display. So the prophecy server issues an HTTP request for the frame's HTML. When the prophecy server receives the response, the server rewrites that HTML. The server then returns that rewritten HTML to the headless browser, as we see on the left side of the slide. Now, the rewritten HTML is going to contain a bit of new JavaScript code, which adds a JavaScript timer to the frame. That timer is going to fire when the headless browser completes the frame load. And at that point, the timer is going to take a preliminary snapshot of the DOM's final state. Now, the timer does this by invoking the pre-existing XML serializer interface. And this snapshot is going to be preliminary because it doesn't include style information, and I'll describe what I mean by that in a second. So anyways, that's what the rewritten HTML looks like. It just has that extra JavaScript timer. So the headless browser is going to start to parse the rewritten HTML, and it's going to discover some tags that reference external content. So first, the headless browser discovers the CSS tag. It goes out and it fetches that. Prophecy doesn't actually need to rewrite CSS files, so that CSS file is going to be passed directly to the headless browser, which is going to process it as normal. The parse is going to continue, and we're going to discover the script tag. Now, the script tag is actually going to be rewritten by prophecy. And so what's going to happen is that after we rewrite that JavaScript, we're going to hand it up to the headless browser and start executing it. But what does the rewritten code actually do? Well, the rewritten code allows prophecy to interpose on all of the object creations and assignment operations that the JavaScript code makes. In other words, the rewritten code allows prophecy to track all writes to the JavaScript heap. So as a very simple example, suppose that the JavaScript code creates an object literal which has a single property named ID. What prophecy is going to do is rewrite the right-hand side of the code such that the object literal is wrapped in a proxy object. Now, proxy objects are official parts of the JavaScript language. A proxy object allows you to define shims, which are invoked whenever someone tries to read or write the underlying object. So prophecy is going to define custom shims, which append the values of each write to a log file. For more details about how this rewriting works, you can see the Polaris paper from NSDI 2016. The rewriting tool that prophecy uses is derived from the one that's described in that paper. So anyways, at this point in the frame load, the headless browser on the prophecy server begins to execute the rewritten JavaScript code. As the code executes, it will create new entries in the JavaScript Write Log. So for example, the code might assign 7 to the JavaScript variable x, and the string hello to the JavaScript variable y, and the Boolean value false to variable z. So now imagine that the JavaScript code finishes execution, and the headless browser resumes the HTML parse. The next tag in the frame is an image tag, so the browser is going to issue a fetch for the image. Prophecy doesn't need to rewrite images, so it's going to hand that image directly to the headless browser. We continue the parse. We fetch the second JavaScript file. We're going to rewrite it as before to track all of the assignment operations. And so we might update the write log to assign the string goodbye to the variable y, and then assign the value 41 to variable x, and then overwrite that variable x again with the value 42. Now at this point, the frame load is now complete. So remember that the rewritten HTML included a JavaScript timer, which executes once the frame load is finished. So the timer is going to fire, and then we're going to generate a preliminary version of the DOM write log using that built-in XML serializer interface. So in this case, that preliminary version of the log will just contain those 4 tags in the page along with their source attributes. So that's how we generate the preliminary version of a frame's write logs. However, much like every caterpillar turns into a lovely butterfly, we must do some post-processing before we can take those initial logs and transform them into the final write logs that the Prophecy server actually sends over to the client. So let's look at that transformation process. So here's the JavaScript write log that I just showed you. And what you'll see is that if we look at this log, the red entries are actually unnecessary. So for example, the variable x is written 3 times, but the client only needs to execute that last write. So in the final version of the log, we just keep the final write to each variable. Now in this particular example, we can eliminate half of the writes that the page would normally make to the JavaScript heap, and this is roughly how many writes we find that we can skip over in real pages from the wild. So now let's take a look at that DOM write log. So what we're going to do is we're going to post-process this log to generate the final version of the write log. So let's step through the differences between those 2 logs. So first, let's take a look at the CSS tag and the image tag in the first version of the write log. So imagine that the CSS tag defines some style rules that affect how the browser will display the image. So what Prophecy will do is post-process the log to inline pre-computed CSS styles to allow the client to avoid having to compute those styles at the page load time. So if we look on the right at the final DOM log, what we'll see is that the image tag has received inline CSS styles. So also note that Prophecy has set the source attribute for the CSS tag to the empty string, since the browser doesn't need to fetch that CSS file anymore. All the styles are inlined. So now let's take a look at the script tags in the original DOM log, as shown by the red boxes on the left. So Prophecy is going to remove evaluation of the full JavaScript files and replace that evaluation with the evaluation of the final write log that I showed you before. So now if we look on the right-hand side of the slide, we'll see that the final DOM write log has empty source attributes for the script tag, because we don't need to fetch those things anymore. So now let's see what happens when a client tries to actually fetch a frame from the server. We have the client on the left and the server on the right. So the client's going to issue a request for the frame's HTML. The server parses the request and then returns a single HTML file to the client that contains a single script tag. So let's step through that. So there's a function called buildDOM, which takes in an HTML string and uses the browser's built-in DOM parser interface to generate a new DOM tree on the fly. The HTML string that we pass in is just the string version of the final DOM write log that I discussed a few minutes ago. So when the client invokes buildDOM method, it's going to actually dynamically create the final state of the DOM tree. So that's great, but we still have to create the JavaScript heap. So if you look at the lower left-hand corner of the slide, you'll see the final JavaScript write log. That's just a series of assignments. Left-hand side equals right-hand side. And so once we do this, we've skipped all the intermediate computation, and the client has successfully loaded the frame. So let me just briefly describe how Prophecy supports client-side caching. The approach is actually pretty simple. So clients are going to persist the write logs that they receive from a server in DOM storage. And so when clients have to fetch a new version of the logs, that is to say when the client has to fetch the frame for a second time, the client's going to include a cookie in the request that's going to indicate the version of the logs that the client has stored locally. So the server says, well, if the frame has changed, I can send the client diffs between the new write logs for the current version of the frame and the version that the client already has stored. So the client can then apply those diffs to generate the latest version of the write logs. And so what's nice about this is that it enables fine-grained caching. So before moving to the evaluation, let me briefly tell you how we use machine learning. We don't, and it feels great, okay? Because we're just smart. We do stuff with our brain, and it just works. So if you take one thing from this presentation, humans first, algorithms last. I'll be taking some machine learning textbooks after the talk, throwing them in a trash can, and setting them on fire. So that's what NSDI needs more of, book burnings. You heard it here first. So anyways, let's now go to the evaluation for Prophecy before concluding. So to evaluate Prophecy, we took a desktop machine and we ran Mahi Mahi. Mahi is a tool that allows you to record HTTP traffic from live sites and then later replay that traffic. So we set Mahi in record mode, we found some live web servers, and then we recorded a bunch of content. In particular, we downloaded content from the 350 most popular web pages. So once we had that content, we rewrote it, giving us a prophecy version of each page in the corpus. So this is the experimental setup that we had. We set Mahi to now be in replay mode, and then we had it serve either the regular version of a page or the prophecy version of a page. So in the results that I'll describe to you now, I'm mainly going to focus on our mobile evaluation results, where the link between the Mahi server and the Nexus phone was either a 4G or Wi-Fi link that was live. And in the paper, we discuss some results with desktops, but I won't really focus on those results too much now. Our optimization comparand was Polaris. So Polaris uses an offline server analysis to derive a page's object-level dependency graph. It looks something like this. So imagine that each one of those nodes is an HTTP object, like a JavaScript file or an image. And so you can think of the arrows as basically saying this object must be fetched and evaluated before the child object can be fetched and evaluated. So during a page load, Polaris server is going to send this dependency graph to the client as well as a scheduling library. So this scheduling library, which is going to be written in JavaScript, is going to allow the client to fetch and evaluate objects along the dynamic critical path for the page. So let's say that the page had fetched and evaluated those blue objects up there. The static critical path is this, just the longest path through the tree, but the dynamic critical path is actually this one. It's the tree that has the most unresolved objects in it, or the chain that has the most unresolved objects in it. So here we see page load time results for a 4G network link, and we compare page load times with the default browser, with Polaris, with Prophecy Online, and Prophecy Offline. So Prophecy Online means that the server generated write logs at the time that the request came in. Prophecy Offline means that the server generated those logs ahead of time before the request showed up. And so what we see is that compared to a default browser, Polaris is going to enable median PLT reductions of 53% and 95th percentile reductions of 67%. And compared to Polaris, Prophecy is actually 2.3 times better, which we think is pretty cool. So what's the explanation for this? Well, one thing to note is that Prophecy uses a single HTTP level round trip to load all of the HTML, CSS, and JavaScript in a page. In contrast, Polaris can overlap some, but not all of those RTTs because the dependency graph might still have serial dependency chains in it. So also note that eliding computation is very helpful. Prophecy can do that, Polaris cannot. So let's now look at median bandwidth savings. Once again, our comparison will be Polaris. So here I show results for both the mobile setting and the desktop setting. And so what we see is that Polaris pages fetch slightly more content than a normal version of a page load. So the reason is that in Polaris, you have to download all the original page content, plus the Polaris JavaScript library and the scheduler metadata. So that's going to add up to roughly 40 kilobytes of data. So in contrast with Prophecy, image size is unchanged. HTML is slightly larger because we're inlining the style information, but JavaScript actually gets smaller by about 25% because of that intermediate computation that we're removing. And finally, in terms of energy savings, what do we see? Well, what we see is that for a mobile phone using either LTE or Wi-Fi, we see very large savings, at least 2.3x or larger for both versions of Prophecy, both Prophecy Online and Prophecy Offline. So before I conclude, let me briefly discuss some related work. My typical approach to related work is let the past die. Kill it if you have to. However, I've been told by my lawyers this is not charitable. So let me briefly discuss two pieces of closely related work. First of all, there's prepack. This comes out from Facebook. It's a JavaScript to JavaScript compiler that identifies statically computable expressions using symbolic execution and abstract interpretation. So prepack is really great if you only have just JavaScript code in your application. But prepack actually doesn't handle things like interactions with the DOM, doesn't handle caching, stuff like that. Shion is another piece of work. It's a proxy-based system that does handle DOM state. The basic idea is that a proxy is going to load the entire page and generate two snapshots. An initial snapshot, which essentially just contains serialized DOM nodes, and then a post-load snapshot, which essentially contains the rest of the page, including the JavaScript state. And so at a high level, there's a lot of differences here, but some of the most salient ones are that shion requires a modified client browser, it doesn't support caching for all state, and it actually can't optimize for interactivity, like ready index. Prophecy actually can. I didn't mention that in the talk today. See the paper for more details. So in conclusion, what did we discuss today? Well, at a high level, we investigated a single question. We said, can a single optimization simultaneously reduce page load times, cut bandwidth usage, and decrease energy consumption? And so the answer is yes. The way that you do that is by eliding intermediate computation. We discussed how the traditional way of building a frame is actually bad because it requires the browser to do a lot of work that gets thrown away. So the good way to load a page is to let the server pre-compute that final frame state so that the client only needs to do the writes that are necessary. And then mobile users can sort of live their life unburdened by the crippling psychological fear of inefficient mobile page loads. So I described a concrete system called Prophecy, which does exactly this. It reduces page load times by 53%. It decreases bandwidth consumption by 21% and cuts energy usage by 36%. And conveniently, it works on unmodified browsers. And on that note, I'll conclude. I'd be glad to take any questions.
If you're coming up to ask a question, please pre-compute any styles or scripts, compress them.
Hi, I'm Shankar from AT&T Research. Great work.
Thanks.
I was wondering if there are pages where the final state is kind of non-deterministic because, the moment there are people impatient, right? The moment they see a page, they want to do something with it, right? So in cases where the final state cannot be predeterministic, will your methodology work?
Yeah, it's a great question. So non-determinism can emerge in a bunch of different ways. So one way you can imagine non-determinism arising is if, let's say, there's JavaScript in a code that branches on math.random or date or things like that. We didn't see a lot of that experimentally in our corpus, but that could certainly take place, right? And so if you wanted to use prophecy in a situation like that, you might, for example, want to force things like math.random to return deterministic values, right, which you can do by sort of shimming the math.random interface. This actually works out, and also you might want to think about making date, timestamp interfaces be deterministic. Now that's going to work fine if the prophecy server is actually generating those write logs on the fly, because, for example, timestamps won't get too stale. But in general, that might be a problem. So that is an issue. You have to be aware of that if you're a page creator. Another thing to note is that web pages in general can have race conditions in them, right? So even without prophecy, I mean, if sort of JavaScript code's coming in slowly, or there's a rendering race between the renderer and the JavaScript engine, you can still get these weird things that happen even without this. So we don't make it worse, but we definitely don't fix it. We don't make it go away.
Hi, Jeremy Elson from Google. This is great work. Really enjoyed it. It's possible to imagine pathological cases, like if you have a loop that creates a ton of DOM elements, it could be the final state is actually bigger than the code that generated it. So I'm wondering how often in your corpus do you see actually negative gains, and also how much faster does this make the machine learning blockchain?
Yeah. Let me answer your last question first. It makes it infinitely faster. I've already formed 4 startups about this, so get in at the ground floor. It's an exciting time to be alive. This is the best timeline. For your first question, in practice, we don't see that sort of adversarial case that you imagine. But that being said, there is sort of like a probability distribution of what types of gains that you get. And it's exactly correct that, for example, like some pages, depending on how the CSS styling gets created, for example, you can imagine that inlining CSS for every single DOM node might actually make the HTML size get very, very large. And in some cases, that might sort of reduce the overall benefits that you get, even if the JavaScript files get smaller. So it is a thing that you would actually want to sort of profile as a page owner to see if, for example, your pages are getting larger. And as we discussed in the paper, too, another subtlety is, what happens if there's a dynamically created DOM node? So right now, we're sort of inlining all these CSS styles. So how do we make sure that new node gets the right style? Well, we have to essentially do some JavaScript layer dynamic styling to handle that type of stuff, to make sure the dynamically generated node gets styled correctly before the user sees it. That can also slow things down, too, right? Because it's going to be slower than in-browser C++ style rendering. So these are issues you have to think about.
Okay, we have time for one more question and 0 more answers. So go ahead.
Hey, Sanjay from Purdue. Great talk.
Thank you.
So I have a big picture question, right? So we we've had a lot of works in recent years talking about improving latency and so on. How much further do we have to go at this point? And do you think we are beginning to hit the limits?
Yeah, it's an interesting question. I would like to think that computer science is actually a science and we are approaching some type of asymptotic optimal. However, my understanding of the Mozilla documentation pages for the web indicate that we are constantly adding new features, which are making things increasingly slower. So I think that one of the big challenges at a high level is that HTML, CSS, and JavaScript are so complicated, and they're not optimized for performance, that we end up having to create all of these like semi-crazy schemes to make things better. So my opinion is that at a high level, the next real frontier for this type of research that's going to really sort of be a game changer is, what's a better scripting language? What's a better markup language that's actually more amenable to optimization and analysis?
Okay, thank you.
Thank you.